So thank you to all of you for joining today's webinar. I am Jorge Rodriguez, engineer at Power Smart Control, and today we will be looking at the case of success, which include a SmartRCP system. So a SmartRCP system is a rapid prototyping system which can be used as a laboratory aid in order to improve, implement, debug, etc., all the controlling algorithm and the control strategy. It can also be used to test all the alarms, the state machines, protection, etc. However, we will be seeing today that it can also be used not only as a laboratory aid, but also as a system that can be used in field to control a real power converter. In this case, a power hub. So thanks to the robustness and the versatility of SmartRCP, it is fully optimized to be used as an on-field system. So today we will see, we will cover a power hub system conformed with a system of three power converters, which deal with PV energy, energy storage, EV charging, and grid feeding. All of that controlled with a single RCP system. So in here, we have a first overview of our system. It will be composed of three power converters. As you can see here, two dual active bridges of 25 kilowatts, a four-leg power inverter of 50 kilowatts. In the middle, they conform a common DC bus of around 700 volts in this case. One of the dual active bridges will be connected to a power of a PV string of around 25 kilowatts. And the other dual active bridge will be connected to a 23 kilowatts battery rack. In the middle, in the common DC bus, we will be connecting several DC loads. And in the output of the inverter, we will be connected the grid and also several AC loads. One of these loads will be the EV charger. So all the system is going to be controlled by a single RCP system. So we will show in a minute, but all of this is enclosed in a 33-inch rack. And the SmartRCP provides the connectivity and the communication, also the internal variable tracking, which we'll be seeing that in more detail afterwards. It also provides or allows remote access and also remote firmware upload. SmartRCP include all the controlling algorithm for the three power converters, all alarm management, and also the state machines for all the three converters, plus also the plant management. In here, we can see a more detailed view of the power stage of the different converters. In the top part, we can see the power stage of the dual active bridge. And on the lower side, we can see the power schematic of the four-leg inverter. You can see in here the four-leg, which is connected to the neutral point and also to the capacitor and the resistor. Here it is the real system. Today, actually, we are connected to this system. So it will be the system that we will be controlling in our demo. As you can see, it's a rack with 4 drawers. In the top drawer is the inverter. The 2 drawers at the bottom are the dual active bridge, the one intended for the PV panels and also for the battery. And in the middle tray, we have the control box and the control system. In here, it is the SmartRCP and also several auxiliary boards, in this case, for powering the high voltage and high current contactors, and also for sensing. We must have an important note here, because all of the details that we will be seeing in today's cases of success were made with a original version or a let's say older version of SmartRCP. So all the IPs and all the user configuration has been done from scratch for this particular application. However, now we have released a list including several IPs which can be used just from the very beginning from the user. So user can speed quite a lot his own development by using them. The very same apply not only for controlling IPs, but also for for real-time simulation IPs. And also, as we will be seeing, we have templates for full converters. So they can be used as an starting point for any project of the customers. We will be seeing that at the end of today's webinar. So today we will be seeing this configuration. It combines real-time simulation with real power converter controlling. We will be seeing that in more depth in a minute, but just to make it clear, all the three converters are enclosed in the rack that we see in a couple of slides before. We will be controlling those real converters, and at the very same time, the SmartRCP system will be performing real-time emulation. That real-time emulation will be used as a digital twin. So the data between that digital twin, which is emulated data, and the data of the real converters will be compared. That provides to us important information about if any issue occurs on the real converter, for example, some power component breaks, or for example, a cable is disconnected, etc., or a capacitor just break. We will be seeing a different tendency between the models and the reality, and we can stop, launch several alarms, etc. Also, we will have access to inner data of those digital twin system. For example, there are data that we can just acquire with the analog sensors because it is quite quick, etc. That is the case, for example, of the switching waveforms or the waveforms across the transformer of the dual active bridge. That data that we will be seeing is the emulated data. Otherwise, all the remaining data that we will be seeing is real data. So all the system plus the real-time emulation has been embedded into the SmartRCP, and the use of internal resources is around 50%. So with this, you can see the real capacity or executing capacity of this solution. In here, it is the user interface console that we have created or custom made for this project. By using the actual version of SmartRCP, user will receive a general use template, which they can just parameterize and make it suit to the real application. So let's go directly with the demo. I will start by taking a quick look at Vivado. Vivado is one tool from Xilinx. Actually, it is BT's tool flow. And that is the tools that we will use in order to configure and also program SmartRCP. In this case, we have several IPs, so we will be covering them. This IP includes all the thing-related stuff, for example, the processing system, reset, GPIOs, etc. This is, let's say, the general one for all sync or all system-on-chips systems. In here, we have a bridge from processor to FPGA side in which we send data from processor to FPGA. Here, it is the opposite IP. So this IP collects data from FPGA and send it back to the microcontrollers. So with these two IPs, we communicate the models and the controls which are performed in the FPGA side with processors. In here, we have the analog to digital converter IP. It is composed for several IPs. This one and this one are in charge or are the drivers for the physical analog to digital converters. They are the ones for the quick channels, which are sampled at 3 megasample per second, and the ones for the slow channel, which are sampled at 500 kilosamples per second. It also includes low pass filtering and also includes several data formatting and also a calculator for RMS values. In here, we have the 3 blocks which perform the control of the 3 converters and also the real-time emulation. This one is for the 4-leg inverter, and it is composed of a controlling system and a real-time simulator. So if we look at the controlling system, we can see actually all the regulators required for the different control loops. Also the DQ transform, as it is a 3-phase system working in DQ frame, it's much easier. Also we have a power measuring block, a RMS calculation block, and the modulating blocks. If now we look at the real-time simulation block, we have all the different models for the different elements of that inverter. For example, the bridge, the inductor, capacitor, etc. For the dual active bridge, we have the very same structure. As you can see, it is composed in this case of a controlling IP and also in a real-time simulator. In here at the top, we have also an alarm block which just make the management of the different alarms that this converter can trigger. About the controlling system, we have the very same structure as before, a regulator, power meter, different modulating IPs. As this one is in charge for the PV channels, we have in here the MPP, the maximum power point tracking algorithm. And in here, we have the real-time simulator, which has the very same blocks as before. So this is just for the dual active bridge, for the some data conversion, etc. This IP is the one in charge to send the data to the data logger, which is the oscilloscope that we will be using in order to analyze internal waveforms. This is the FPGA to microprocessor axis bridge that we mentioned before. This one is in charge to modify or controlling the panel LEDs, digital inputs and output, and this PWM cluster is just an additional security block which enable or disable the PWM signals, so we can have it as an additional security measurement. So this is the Vivado structure for controlling this system. As I mentioned before, this was made before general user IPs were released, so users can use that IPs in order or as a building blocks to create his own system. So they will they can speed it too much. So now we are going to look at the user interface. This is it. In here we have at the top 3 blocks, one per converter, one for the 3-phase 4-leg inverter, another one for the PV dual active bridge, and another one for the battery connected dual active bridge. Commands and options are quite similar to all of them, but obviously depends on the converter. we have here a button to enable or disable the converter. In here, we have a button which allows us to configure the real-time simulation parameters. You can see this is the plant that the emulation is performing, and in here we can vary in real time of all those parameters, so we can actually fine-tune the emulation. This one is in charge for the temperatures. This one is for the controlling parameters. So in here we have the modulating parameters, for example, switching frequency, grid frequency, etc. And the parameters for the regulators, for current loop and for voltage loop. In here we have a compensation window which allows us to compensate the analog to digital gains and offset that are between the sensor and the number that we receive at the FPGA side. So with this correction, we can just get the very same number that is measured by the sensor here in the FPGA side. And in here, we have the alarm limits. That means that there are several configured alarm steps, and if any of this magnitude is outside this limit, an alarm is triggered. In here, we have one status bar per converter. So we have in here the actual status of the state machine. As you can see, all three converters are stopped, armed, and ready to be enabled. In here, we have all the report for previous states. And in here, we have a report for the previous alarms. At the right part, we have several graphs in order to see the energy balance of the full system. So that is the main tab. In the four-leg inverter tab, we can see the power, both active and reactive, of this converter, and the DQ references. The very same applies with the dual active bridge, in which we can see the input and output power, input and output currents, and also the phase delay, and the very same for the one of the batteries. For the dual active bridge also, in here, we have the button in which we can parameterize the performance of the simulator. In this case, as you can see, this is the solar PV, the PV dual active bridge. So we can modify the PV model, and the very same will apply with the battery, but instead of the PV model, we will have a battery model. So let's start the system. So we enable the inverter. As you can see, it is connecting. Let's connect the PV dual active bridge, and the very same for the batteries. Is on the go. As it is a real converter, it's not quick. I mean, it's just a soft start. In the meanwhile, we can check at the data logger. In here, we have two graphs. In this graph, we can select up to 6 waveforms, which we can choose from all this list. And let's take a look first at the inverter. For the inverter, let's check the three-phase voltage and also the three-phase current. I'm going to change the sampling times to 10 microseconds. We are going to update and enable. As let's move a little bit the trigger. Yes. So in here, we are seeing the grid voltages and also the inverter currents. I'm going to fix the axis. So from 40 to minus 40 amps and apply. And for example, let's change the the voltage of the inverter. In here we have 600 volts, so let's change it from 700 and apply. As you can see, current has increased. If we set it at it was before, current goes down. For example, let's now check something a little bit more interesting. For example, the modulating signals, which is modulating A, modulating B, and modulating C. Let's apply that. In here, you can see the actual, sorry, let's move a little bit the trigger. The actual waveforms which are inserted to the modulator. As you can see, they has the harmonic injection, etc. All of this is real data. However, let's see about the dual active bridge. In the dual active bridge, we are going to check the inductor current, the voltages across the transformer, so primary voltage and secondary voltage, and the input and output current of the dual active bridge. And this one, let's put it unconnected. So as the dual active bridge is switching at much higher frequency, we have to move it down to 60 nanoseconds. So this is a 60 nanosecond sampling time. So we apply that. And as you can see in here, we have the voltages across the primary and secondary, and also the inductor current. This data is emulated data. I mean, data acquired from the digital twins or from the real-time simulators. This is the only data that we have seen today that is emulated. All the remaining data is real data. As you can see, for its frequency, by using analog sensors, we won't be able to acquire this type of overview. That is the real magic of one of the magic of including digital twins or real-time simulator together with our controlling states. In here, if I just, for example, change the power reference, which is now 50 kilowatts, if I switch it to -15 and apply, you can see how current is changing from positive to negative, and how the voltages across transformer has changed, and also its current. If I set it as before, you can see it again. So this is the demo of today. And I would like to go back to the slices and give just the last concept. We have seen how SmartRCP can be used for both as a rapid control prototyping. I mean, a system which is capable of performing controlling of converters, both as a laboratory level or, as in this case, as an on-field converter controller, and also how it can include real-time simulator and digital twin capabilities. So this is the powerness of this system. In the basic configuration, we provide the hardware unit, which is this white box. Also, a template with all the drivers, a full template of a converter, in this case, a buck converter, which also includes a small PCB with the converter already installed. It is a small converter. Also, several IP cores, in this case, control ones, for example, the modulator, PID, etc. The waveform viewer or the data logger, and a user interface which can be parameterized by the user. So user can add some field, can remove them, etc. As optional resources, we offer additional controlling IPs, let's say advanced IPs, IPs for for real-time simulator, which can be used as a digital twin, templates of full converters, for example, we can say the Vienna converter, dual active bridge, etc., and advanced support access. In here, we have a list of the different configuration of IPs. For example, in the basic configuration, which is already provided with a SmartRCP, we have a modulator, carrier signal, PI and PID regulator, some filtering IPs, RMS calculator, dual active bridge modulator, etc. In the controlling IC packages, we have several IPs, let's say, orientated to three-phase converter. So we have DQ transform, PLL, different modulator, etc. Active and reactive power calculator, etc. Also, in the controlling template packages, we have already made templates to control full converters. So that is the synchronous buck converter, which is already included in the basic one. And we have also the dual active bridge converter with two different modulation strategies, SPS and TPS, three-phase dual active bridge, a three-phase inverter rectifier with 3 legs or 4 legs, as we have seen today, Vienna converter, Alhambra, which is fully developed inside PSC. This is a proprietary converter, full bridge, and all extra converter. Also, as real-time simulator model, we have the battery model, the PV panel model that we have seen today, electrical grid, also seen today, several power motors, both permanent magnet and asynchronous motors, dual active bridge emulator, inverter emulator, those has been used today, Vienna emulator, and also we have models of power components, in this case of a MOSFET and also of a GFET. So this has been the content of today's webinar. I would like to emphasize how a SmartRCP system can be used as a controlling system, as a rapid controlling system, but both at laboratory level and also in field. So you can with them control real converters. Also, this platform is not unique for controlling, but also it enables real-time simulator. And if you join both real-time simulator and controlling, you can create a digital twin, which will, let's say, provide a new world of possibilities.